Last year, 200,000 people were hospitalized and 38,000 people died in the US from influenza. Now, epidemics can be controlled if you get vaccinations and information to the right people quickly enough. Lab results take between 1 week and 2 weeks to get from the labs to the Center for Disease Control in the US, where they can then act on it. Vaccinations take about 2 weeks to become effective. So you can see it's vital to be able to use external sources of information outside of their own labs to be able to help them to predict what the current rates of infection are and which places need the vaccinations first. In 2012, a group of researchers, and actually there were a few different research groups, did some analysis over Twitter data. They did some machine learning and then filtered the Twitter feeds, built a prediction model, and then this graph shows their predictions versus the actual outbreak. And it's actually pretty close. This allows that immediate forecasting, especially combined with the CDC data, to help predict where to put vaccinations. But we'll see later on that historical matching doesn't necessarily provide perfect prediction. Early in 2012, a man stormed into a Target store in Minnesota in the US, waving a flyer. I went to see the manager, and he said, "How dare you send this to my daughter?" The flyer had ads for cots, for baby gear, for dummies. He said, "You're encouraging teenage pregnancy." The manager apologized. "I'm sorry. Won't happen again. I'll talk to my management." No. 2 days later, the manager called up the house just to make sure that the father was okay. There wasn't any repercussions. And the father, rather abashed, said, "It turns out that there's been some activities in my house that I wasn't aware of, and my daughter's due in August." Oh, coincidentally, Target in 2012 made $20 billion in profit, and other retailers are going broke. This is a visualization of the square kilometer array. This is a radio telescope that's going to be built in outback Australia and throughout South Africa. It's a huge project. It's going to produce 1 square kilometer's worth of radio telescope sensitivity, which is 50 times greater in sensitivity than anything currently on Earth. It's going to have 10,000 times the speed of anything currently on Earth. And any ideas how much data this might be about to produce? Maybe terabytes a day? 10 terabytes a day? Maybe a petabyte a day? 900 petabytes every day. That's a lot of data. This is probably one of the biggest big data problems that we're going to be seeing in the next 10 years. Well, my name is Martin Grinnell. I'm the Chief Data Scientist at Applied Data Science. The past 6 years, I've been working as a quant analyst in the finance world, modeling the markets, crunching huge amounts of market data. And prior to that, I was a .NET architect consultant, or solutions architecture consultant, working for Redify, and then prior to that, various other industries. First time I talked at TechEd was in the US 8 years ago. At that time, I was talking about the best ways to build structures and build programs and processes to output lots of data. Then 2 years ago, I was talking back here, and I was talking about the reactive framework, complex event processing over streams of data at very high speeds, and using that to do automated trading systems. And now, for my day job, I work trying to build data science capabilities in organizations. And outside of work, I'm a dad. And this picture up there is the last trip I did to Bali, when we managed to leave my 3 wonderful children with my mother, escape for 5 days. I think it's the most relaxed I've been in 10 years. So what are we doing in this session? I want to provide you a roadmap of how to implement big data in your organizations. We'll look at implementing some streaming infrastructure. We'll even look at how can you build a real-time web dashboard using Signaler, talking to some real-time analytics on the way out to the big data. We'll have a look at some of the pitfalls, some of the dangers of when you're implementing a system like this. At the end of the session, we'll talk a bit about data science and some of the things you need to be very careful of when you start to do the data analysis itself. And then at the end, I'll take questions and hopefully give you some answers. Let's start with what is big data and why should you be bothered about it. Is it just hype? This is a Google Trends chart of the term big data, searches for big data, versus searches for data warehousing. And as you can see, the blue line is obviously big data. Over the past few years, interest has exploded in that term. And data warehousing, not so much. Well, that just says what people are searching for. What does Gartner think? Gartner are thought leaders in technology strategy. And who here has seen the hype chart before from Gartner? We've got a few? Yeah? Okay. This is a very nice chart where they try and plot for each technology that comes out, major technology, the flow of that technology and what they think the positioning currently is for that technology. So it starts off with a technology trigger. Someone creates some technology or some basis for it. Then it gets hyped. The hype machine comes in, media picks it up, the expectations get hugely inflated of what it can do, and then it doesn't deliver. There's a trough of disillusionment. Then over time, people actually work out how to fit that technology into their current processes. And then the plateau of productivity is where that then becomes a useful technology. Now what's interesting about this chart, I've scrubbed off a few of the items on here. Big data is right up there at the top of the hype. But the components of big data, such as predictive analytics, such as text-based analytics, in-memory databases, cloud computing, are all on their journey through to that plateau of productivity. Well, that's what other people think. Let's define big data. You may have heard of big data in terms of the 3 V's or the 4 V's or the 5 V's or as many V's as you can say. Let's start off with the 3 main ones. Volume. Nothing is specific about what makes a big data project in terms of volume. It's to do with your budget, to do with how much data you can comfortably deal with in your current systems. It might be gigabytes, petabytes, 900 petabytes a day. In the case of retail systems, you suddenly get all the clickstream data, all the behavioral information that you can find. The second V, which is very commonly spoken about, is variety. Variety here is the ability to bring in both semi-structured data, data which comes from other sources which you do not control, and even your own varying schema, being able to bring those together and handle them in one place. A great example of that is the CDC, and the ability to use Twitter data or Google search terms to help enhance their own internal data systems. The third V you may have heard about is velocity. And nothing speaks to velocity greater than, for example, the Murchison telescope, which is a precursor to the Square Kilometre Array. This actually went live in June, and these guys ship from Murchison to Perth, and then out to all the universities, 400 megabytes a second. And they're currently doing it over the NBN, the National Broadband Network, at least at the moment. Now, the fourth V is a little bit controversial. This one is veracity, or truthfulness. If you have a large amount of data coming at you very fast and coming at you from multiple sources which you don't necessarily control, you are not going to be able to clean that data. You can't guarantee the quality of the data going into this distributed data mart. So you have to be able to cope with bad data. And you have to know what sort of quality your data is so that when you make these business decisions based on this data, you have some level of confidence in your results. So these four V's make up what I consider to be a big data problem, if you have these four aspects. Another way to think about what data we want to process is by going back to 1983, which seems to be the favorite time span for this conference. In 1983, if you were a grocery or a supermarket, you would have maybe a product inventory system with a count in there of how many items you have on the shelf. And when people bought products, they'd come to a cash till, which was really a glorified calculator with just a shelf in it. And every night you'd go and check the inventory. So we'd be storing a very small amount of data, just for product data. Fast forward 10 years, and we start to capture transactional information. We start data mining our behavior, the purchasing behavior of our customers. For example, Dan Murphy's in Victoria had a whole series of stores, had a couple of stores in the city. They were looking at their numbers, and the two stores in the cities had the most sales, but didn't have the most revenue. And they were saying, what's going on? Why is there such a difference in behavior between these two stores and all the rest? And it turned out that those two stores had the most single can sales. People just going in and grabbing a can and heading out again. So they took that knowledge, they changed their advertising strategy, and it was very effective. Nowadays, who here has got a store loyalty card of some kind? Well, most people, I assume. You have become a source of profiling information to those businesses. Every purchase you make at the grocery store, every time you go to fill up your petrol, that's all feeding in to a model about you that can be effectively analyzed by those businesses. And this is the sort of data that we want to capture now, the sort of data that we have the capability to capture now that we couldn't capture in the past. So if you receive a flyer in the post trying to sell you baby clothes or dummies, it may be time to talk to your partner. Right. Well, let's have a look at how we actually implement one of these systems. We'll start off with a very simple architectural diagram of an application that you may have at the moment. Most applications have got a front-end app, whether it's a mobile or a website or a desktop app, usually talking to some set of middle-tier services, and then those will feed into some transactional database. From there, it feeds to a reporting database, and you'll have a dashboard or reports that give you the status of your current business. Notice that we've got the logs up there. Now, these logs are typically used for auditing purposes, or maybe if there's some problem, the business gets involved, or the IT crew get involved and try and find out what's going on. But usually, they're not used to help improve business, or improve the business. So let's start trying to add more behavior into our data that we can manage. Now, I've kept this slide extremely generic. We're going to have some kind of pre-processing step. Typically, that would be an ETL in a traditional data warehousing process, extract, transform, and load. However, when we're dealing with big data, we actually want to minimize the emphasis on the transformation. And in fact, minimize the emphasis on the extract. We'd like to have stuff just coming to us, and we then flow it upstream. What we do emphasize, however, is real-time analytics, so real-time analytics over that in-flight data to get some idea of the quality of the data. And the other aspect we emphasize is anonymization, or removing personally identifiable information. Once the data leaves that pre-processing box, we then need to manage somewhere, or we need to have somewhere to store it. And the key with the distributed storage that you place this information in is, one, you want it split over lots of hard disks. Well, that's the same as any kind of SAN storage design. But secondly, you want to have it close to your CPU. So ideally, you have a cluster of CPU and disk nodes, if you're doing this on-premise. If you're doing this in the cloud, you can store it inside a Hadoop cluster in the cloud, or you can store it in some kind of cloud storage provider, like Azure. Once we've done that, there are typically then two ways we process that data. One is for ad hoc querying, and I'll show a little bit of that later on today, and also in a batch process, which we can then feed into our internal data warehouse. Okay. Well, let's have a look at what Microsoft brings to the table in those different boxes. And then we'll go into a demo of showing some bits of those connecting together. First of all, we have our sources of data. Now, actually, this slide comes from a paper written by the Patterns and Practices group. They've got a best practices on Azure paper up in Codeplex. And they have section 4 of that discusses big data in Azure. And it's a very good read. I've got that in the resources at the end. So we start with the data sources. And then that pre-processing step, we need to use some kind of ETL tool. Most of you, I assume, will be familiar with SQL Server integration services. There's also a product called Data Quality Services, which can plug into that and help you manage your data quality as it's going through that box. And another piece in here is Stream Insight. Now, I'm particularly fond of Stream Insight. Last time I spoke was about reactive technologies and complex event processing. So this is very dear to my heart. This allows you to do analysis of your data and get some idea of the quality. Once we've pre-processed it, we need to work out where to store it. Traditionally, that's been SQL Server in the Microsoft stack. There's, in fact, a product called SQL Server Parallel Data Warehouse, which is an appliance, big appliance, that you can wheel on site. And that is trying to do big data on site using SQL Server and other tools. There's actually a talk about that later on this afternoon, if you're interested. For this talk, though, I'll focus on Hadoop. Now, what is Hadoop, apart from a funny name? Hadoop is a managed, Hadoop is a set of, it's a whole mixture of stuff, right? It's basically a set of job tracking software to track distributed jobs. It's a file system. It's also a map reduce engine I'll talk about. It's also a whole lot of other little tools all bundled up together. It's a whole ecosystem of open source tools. Sometimes it feels like it's sort of stuck together with a bit of sticky tape and glue. But it is very popular, and it works. And it helps bring computation close to the data. And which is why Microsoft has picked that up as the basis of their platform for big data in the cloud. Now, when you're storing in Hadoop, you have three options. One is you can create a cluster on-premise, and you can store your data there. The other option is you can spin up a cluster in the cloud, and you can store your data in native HDFS, which is the file system of Hadoop, on that cluster. The third option is you can store your data in Azure blob storage, which can then get accessed by a spun-up cluster. Now, a word of warning. If you store your data in a cluster on Hadoop in the cloud, you're paying for those machines to be on. What do you think happens if you deprovision the cluster and stop paying for it? Any ideas? What's going to happen to your data? So the recommended strategy is you have two choices. You can keep a cluster running all the time, or you can store your data in Azure blob storage. And then when you want to process it, spin up a cluster, process it, and shut down the cluster. And that's actually the recommended strategy. Once we have the data there, we can then process it, take it back into our corporate data models, then expose that in SharePoint, or Excel, or SQL Server reporting services, or our own applications. Who here went to Peter Meyer's talk earlier on this morning? Is there a few hands? OK. There's some very interesting technology around the visualization piece that's happening in Microsoft. And we'll show us a very, very small fraction of that, but that's not really the major focus of the talk. OK. I'm going to put on a different hat today. Imagine I am a spin doctor for an electoral party. And my job is to make sure our advertising spend goes the right place. I want to know what people are saying. I want to know when they're saying it and where they're saying it. That's my job. So I'm going to use big data to solve that problem. I'm going to use Twitter. And I'm going to take the Twitter data, and I'm going to feed that into Stream Insight. Then, I'm going to go out to another service, get some external data, and enrich that with sentiment analysis. I was going to say, is it a happy tweet, a sad tweet, neutral tweet? Then I'm going to fan out my data. Firstly, I'm going to send it to a real-time dashboard. Why? Because when the PM comes into my office, taps me on the shoulder and says, Martin, how are we doing today? I can point to a web dashboard and go, look, this is real-time information. This is what people are saying. I'm also going to feed it up to an Azure database. Take some metadata, which I can run my SQL reports from. And thirdly, I'm going to stick the raw tweets into blob storage. I'm not going to transform it. I'm not going to strip it. I'm not going to pick up just some fields out of it, because I don't know what I need. And then once it's gone, it's gone. You can't capture it again. So I'm going to take the whole lot, dump it into blob storage. Once that's done, I now have a bit of an issue. I want to work out what people are saying, but I want to know if it's Labour supporters or Liberal supporters who are saying it. So now I need some machine learning. I need something that's going to classify all my users between the two parties on a two-party basis. So I'll do that using a combination of Hadoop and other technologies. Once I've done that, I can then visualize the information. So let's have a look at the start of that process. Now, this is a bit of a change in level of abstraction. We've been talking very generically, we've been talking about processes. What I want to do is actually dive right down and give you some feel for how this works at the bare metal level, at the code level. So this is Stream Insight. And actually what's important about this is where the code comes from. This is from a project called Twitter Big Data, the original source code, which I then modified and forked. And it's a great example of pulling all this stuff together. I thoroughly recommend that you go there and have a look at it. Stream Insight is a product from Microsoft that is licensed along with SQL Server. You get it for free with SQL Server. It can run either as a standalone server, or it can be embedded into your own applications. In this particular case, I'm embedding it into a console app. Now, Stream Insight works with the concept of sources of data, queries, and then sinks of data, or sinks where data go into. So in this case, we're going to be using link to Twitter to define a stream of data which is going to be coming back, and it's going to pull back all tweets which contain a certain set of keywords. The keywords I've chosen are election-related keywords. Once we've done that, we can then start applying queries over the top of those streams. And these are queries over live data. It's not like queries over a database. It's a similar syntax. It's still link, but this time we're doing it over live streams of data. So in this case, I'm going to filter out any offensive words because this is being recorded, and I don't want tweets appearing on the screen with certain words in. The second query is slightly more interesting. It's going to start generating some windows over our streams. So in this case, a tumbling window means every n seconds. So we're going to create a window every n seconds. And when that gets fired, we can then do some computation over all the events which happened in that window. This is very, very powerful. Right? You want to be doing windowing functions and doing analysis over your data. You want to look at standard deviations. You want to look at how much variety you're getting. You want to see if people are hitting your web server from a single IP address, if someone's trying to screen scrape your website, someone's trying to overload your systems. Those kind of analytics you want to be having before you start putting this data out into the cloud so you can capture the problems right at the start. So here we have tumbling window, and we're going to create a tweet summary which has got the count and the average sentiment of all the tweets flowing through. This one is slightly more interesting. We're now going to group. We're going to take that stream, we're going to split it into multiple streams, and then for each of those streams, we're going to do the same thing. Take the count and take the average sentiment. Once we've got our queries, we then need to define our sinks. So first of all, I'm going to take the raw data and put that into my local Hadoop. And in fact, there's a version of HD Insight, which is Microsoft's Hadoop platform, which runs for development purposes on your laptop, in Windows 8 or on Windows Server. Secondly, I'm going to take all my tweets and I'm going to go and store them up in blob storage. So I can then use the cloud to process all those tweets. And thirdly, I'm going to take those tweets and stick them into Azure database. Just the metadata from them. And then we get to something a little bit more cute, which is I'm also going to, in the demo, host a web server in my console app, host SignalR, or Signaler, depending on how you pronounce it, and then allow my real-time dashboard to connect to that and see these tweets and see the information flowing through. And the actual adapter to do this is tiny. So they've done a good job with the abstractions on Signaler. Okay, let's run this up and see if we actually get any tweets. Okay, good, we've got tweets flowing through. Well, let's run up the dashboard and see what people are saying. Okay. So let's see what we're getting. So we've got 10 tweets a second. Things are getting quite busy at this time of the season. We got Rod and Abbott both with 2. So the scores for sentiment go between 0 and 4. Okay, we should now have some data in our system. Let's go and check that we've actually managed to save the information. There we go. Okay. There we are. Now, a tweet you would think is pretty simple. There's actually a lot of information in a tweet. Let's have a look and see how we can process that. Well, I've also got it stored in Hadoop. So here's my Hadoop node on my local machine, and we should have some information in there as well. So this is the capture part of it. I'll look at 3 bits: the capture, processing, and visualization. Before I go on to the processing part, I'm going to explain a little bit more about Hadoop. So HD Insight is Microsoft's Hadoop platform. And that's HD Insight in the cloud, or there's a version for local development purposes on your Windows box. That is based on Hortonworks data platform, which is itself a compilation of all the open source Hadoop tools, packaged all together, where the versions match and tested, making sure it all works. Hadoop, or the core of Hadoop, is really 2 pieces. There's a file system, HDFS, and there's a MapReduce engine. MapReduce, who here knows what MapReduce is? Okay. MapReduce is a very simple algorithm. All it says is we take some data, a set of records, and we'll apply a map function from those records to produce a whole set of key value pairs. Okay. Then the engine will sort those key value pairs, and then we'll supply a reduce function, which, given a key and given the set of values, outputs one or more values itself. That's all it is. That's the algorithm. The reason why it's so interesting is that it turns out that a lot of problems in software and algorithms can actually be reduced to a set of MapReduce steps. It may be many MapReduce steps, but for example, relational algebra, which you use for SQL, can mainly be reduced down to MapReduce steps. And the other nice thing about MapReduce is it scales really well. And that's why Hadoop works really well, because you can throw lots of cores at it and lots of disk at it. Now, I said there was a bunch of stuff in Hadoop. And this is just some of the bunch of stuff that you can use. And there's more bunch of stuff being created every single day. If you look at the list of projects which can use MapReduce and Hadoop, it's just growing. It's almost like a pipeline. You've got a whole load of projects appearing over here, and a whole load of projects quietly just disappearing over here. But the core of Hadoop has got enough traction that there's value in using it. I'll briefly mention what some of these do. Pig. Pig is a procedural or imperative-driven data analysis language. What it does is it translates a language called Pig Latin into MapReduce jobs, and then runs the jobs. Scoop is an import and export tool for exporting to relational databases or importing from relational databases. And it converts the queries into MapReduce jobs. Oozie is a workflow language, similar story. HCAT and WebHCAT are job control management systems which sit on top of the Hadoop ecosystem. And Hive, which I'll talk about a bit more, Hive translates a SQL-like language to MapReduce jobs. And the good thing about Hive is that there is an ODBC driver for it. So what this allows you to do, the problem with MapReduce and Hadoop is it's Java-based. So if you want to write a MapReduce job to run inside of Hadoop, really you've got to either write it in Java or you've got to use what's called a streaming API, which is a pain in the neck to use. So there's lots of Java involved in there. The benefit of abstractions like Hive and Pig is you can use your standard abstractions you're used to, such as SQL, to generate these highly distributed queries. With an ODBC connector, you can plug into it from Excel, SSIS, from reporting services, from Tableau, from any other system. Okay. So Hive. This is not going to be a introduction to Hive talk. So we'll only do a couple of things in here just to prove the point. Okay, Hive. This is a SQL Server Management Studio for Hive. You will have to get used to text log files, consoles, scripting, if you want to dive into this in depth. Actually, make sure that's done. Okay. Now, if I go back to where I've got the information stored, I've got it stored in a directory called ospol raw and then today's date. There's a whole load of tweets, and it's just the raw tweet files. What I can do is tell Hive to treat that whole directory as if it was a table. So, and then I can do a SQL query, sort of. So that's picking the top 5 tweets out of that directory. So what gets more interesting is if we want to, like that information we're not going to give to a business analyst. So let's just get the screen name and tweet ID from that. Okay. What's going on here is there's a series of operators we can use over that raw data. And what this is going to do is parse the data, load up the JSON object, and extract the property called ID. And similarly, it's going to load up the user object from the JSON, and then extract the screen name. What it's doing is actually running a MapReduce job, as you can see here. So it's converted that query into Java, compiled it, and then run it under the MapReduce infrastructure. Now, it actually supports a huge amount of SQL, and it also supports the ability to plug in your own deserializers under the hood, and supports compression, and there's a whole load of other things it does support to make it very useful for business analysts. And very briefly, one of the nice things that Microsoft has done is created wrappers to allow us to generate .NET MapReduce jobs. So if we want to go directly to the MapReduce infrastructure without writing in Java, we can now do that really very simply. There's an API, or sorry, an SDK, which is the Hadoop SDK, which allows you to create a MapReduce job by simply deriving from Hadoop job, passing in the mapper class, the reducer class. You say connect to a Hadoop cluster and run. It packages it all up and runs it for you. Not a line of Java inside. Okay. So that was processing. Very quickly. And we'll see the visualization towards the end of the talk. I want to play a quick game. We call it Risk Pictionary. Who here has played Risk in the past? It was one of my favorite games when I was younger. A few? Yeah. I'm going to show you a picture. I want you to think about what risk to the business that picture might represent. Then I'll give you some mitigations of how to manage that risk. So let's start with this one. Have any takers? It's a bit obscure. Oh. Okay. Privacy. I was speaking with Gary Potts, who is the screening center director. Oh, sorry. This is Gary Potts, who's the screening division project director at the Cancer Institute of New South Wales. He gave a talk down in Melbourne at the Big Data User Group. He has an interesting situation that he's got a lot of data to manage. He has to respect the privacy of the patients absolutely. He cannot have any leakage of information, and they cannot have any errors in their data processing. But they also want to enable as much research to help cure cancer as they possibly can. That's a pretty tough call. So I talked about and asked him how they do that, and they annotate every single patient record with exactly what level of access that's allowed and what types of research are allowed to be done over that data. Now, the best way to handle PII data, personally identifiable data, in the cloud is don't store it. If you really must access information and do analysis at the individual level, then strip all of that out, put it into some local internal secure database, and then upload the stuff to the cloud. And that's why I was saying do that in the pre-processing step. Now, when Hadoop was designed, which was by Mike Caffarella and Doug Cutting, Doug Cutting, in fact, was one who named the Hadoop project. It was his son's name for his his yellow elephant toy. They called it Hadoop when he was a toddler. Well, when they designed Hadoop, security was not a big issue. In fact, there was no security. In 2009, they added Kerberos authentication and then some authorization into the file system. But it's still pretty weak. There's a project called Intel Rhino that tries to make Hadoop a bit tougher. However, there was one group to whom security was actually important, and they're called the National Security Agency. You may have heard of them. So they built a product sitting on top of, they wanted to use Hadoop, they wanted to use MapReduce, they wanted to use HDFS. They built a product called Accumulo on top of that platform that does have security right down to the cell level. So if you need that, you can look at that project. Okay. If you were to strip out all the PII information from your data, if you got rid of everything that you think possibly could be of an issue, and you upload that out to a big data repository, and then you give it out to the public to do some analysis, who here thinks that that's probably, you should be safe, right? There shouldn't be any callback on that or any issues. It should be safe. You've done everything you possibly can to make sure that nothing's going to go wrong, no one can be identified through it, right? Well, in 2009, Netflix put out a competition. It was a competition to try and improve their algorithm. And what they did was they took the viewing history of all their users, stripped out all the PII, and made it public, and said, we'll give a reward to anyone that can improve and best our current algorithm. And in fact, they got a 10% improvement. They were really happy about it. What they weren't so happy about was they also got a lawsuit. And the lawsuit was kind of interesting. The lawsuit was that someone's sexual orientation could be determined through the history of what they were viewing. And the way that worked was, turns out, people were posting on the Internet Movie Database, not anonymously, about the movies they were watching. So there was this bank of data from Netflix, which was anonymous, which had the full history of every user. There was the non-anonymous information in IMDb, or the postings of what they'd watched. And some researchers correlated the two. And through that, they could work out that, okay, this person watched it there, and so therefore they'd also watched all the rest of these movies. And because of that, that determined some information about them. And Netflix lost the lawsuit. They had to pay out $9 million, of which $30,000 went to each of the two plaintiffs, and $2.2 million went to the lawyers. Okay. Who can guess what this one's about? Cost. How do we minimize the cost of doing all this stuff when we've got big data? Well, one of the first things you have to decide is where you're going to store your data. You can store it on-premise, you can store it in the cloud. Are you going to manage your elasticity yourself, or are you going to get someone else to manage it? Anyone here heard of ClickFrenzy? Yeah, a few? Okay. ClickFrenzy was a great idea of bringing all these retailers together, like these big days when everything was going to happen in a single day, everyone buying lots of stuff. They managed their own elasticity. They had their own cluster. In the first 10 minutes, the elastic broke. Now, CloudFrenzy v2 went off without a hitch. And that's because they moved to a cloud hosting provider. What do you think about that? Okay. Let's assume that you do use the cloud. How do you reduce your operational costs? Well, the best way to do that is to sample the data, obviously. 1 to 100 sampling, 1 to 10,000 sampling. One thing you need to be careful about is that you don't undersample minorities in your data. So a technique to manage that is called stratified sampling. And that's where you basically upweight minorities in your data. Then the other issue with sampling is you've got to be very careful about your algorithm you use. Because even though you've got this great distribution capability, if you have an algorithm which is the order of not n squared, like you're correlating the data from every user with every other user, that might work fine on a development machine when you've got your data scaled down 1 to 10,000. However, when you put that in the cloud, even with the infinite scalability of the cloud, it's either going to take a millennium to run, or it's going to cost you an absolute fortune. This picture is often associated with what's termed the longest traffic jam in history, which was a 10-day traffic jam in China. People were actually starving to death in it. The picture's actually a fake, however. It's actually photoshopped. But this is what your infrastructure can look like when you start capturing all this big data and start flowing it over your own networks. So you have to be very careful about how you do that. Obviously, use compression. Obviously, use big blocks and send it up to the cloud providers. One thing that's I find kind of interesting, you have to work out what size your blobs are going to be. Now, if you're using Hadoop, Hadoop works really well with large-sized blobs of data. Because what it does is it partitions it up and says this part's going to go over here, this part's going to go over there, this is going to go over there. And so the recommendation is to have big blobs of data. But in Azure, the speed limit on reading a single Azure blob is 60 megabytes a second. The interconnects between the cluster and the Azure blob storage is 10 gigabit per node. Right? It's not even shared, it's actually full 10 gigabit connection interconnect. So if you want to maximize your interconnects, what you want to do is you want to make sure you have at least 10 blobs. Right? So split your stuff up into at least 10 blobs, and also use compression. That will maximize your throughput coming from Azure blob storage into your cluster. Okay, I'm sure everyone here is familiar with Murphy's Law, right? Especially speakers in the room. I assume most people here are familiar with Moore's Law about capacity, or actually number of transistors doubling every 2 years. But a show of hands for who's familiar with Parkinson's Law? No? Okay. Well, Parkinson's Law can be paraphrased as, no matter how much you earn, your partner can always spend it. Now, all three of those are relevant to big data. Your infrastructure will go down. The amount of data you're capturing will double or triple or quadruple. And no matter how much infrastructure you have, you're always going to fill it. Right? Your bandwidth will always be full. So you have to use a queuing infrastructure when you're pushing stuff from inside your infrastructure to the cloud. Now, we've used various ones. One of the last ones used was RabbitMQ, which we found very good. We did have one scare, however. The last time I was here, I was talking about an automated trading platform that we had. And the trading platform tended to work hardest at the end of the day. We used to open up all these positions, and then the last few minutes of the day was when we'd be frantically trying to sell. And we didn't want to ever get caught with holding stuff. We needed to make sure we were closed out by the end of the day. And we turned on all this behavioral analysis, all this debugging information was flowing back, and our main systems were running at the ASX, actually a co-located site just next to the ASX. And so you don't get very big pipes from there. And you can probably guess what happened. Everything got busy, all the data flow started coming out from there, it swamped the network, it swamped our connections, and we actually lost sight of the whole thing for about 5 minutes. 5 minutes may not sound like a lot, but when you're right at the end of trading, it's a long time. So after that, we implemented a quality of service. So make sure that you have quality of service that has lower guarantees over your big data capture, your behavioral data. Okay. This is the last slide in our Pictionary. This one is a little bit abstract. This one's a little bit curly. This is a beautiful frozen waterfall. I liken this to analysis paralysis. Or in other words, data warehousing projects gone wrong. The approach where you have 10 business units and you're going to build the data warehouse to rule all data warehouses. You get all the heads together You start working out common schema. You start working out the semantics of your data. You start working out the semantics of your data. What's the cardinality of your entities? You get the BAs involved. You ask them, what queries are you going to have? Because we need to know so we can build the dimensions out. What aggregations do you need so we can optimize the performance of this? Because it's going to take us a long time to load this stuff. We have to make sure that you can query it in fast time. 6 months goes past, 9 months goes past, 12 months, you finally have your data warehouse. They start doing some queries, and they go, yeah, that wasn't actually the query we wanted. Something else. So you want to have governance, but you also need to have agility. And in fact, this sort of goes back to the keynote where they were talking about responsive organizations. You need to be able to respond and query very quickly over your data. And to me, this is why Hadoop is exciting. This is the key. This is where the elasticity in data processing makes such a huge difference. For once, we can store our raw data out there, and then we can just query it. Well, it doesn't sound very exciting, but what it allows us to do is we don't have those steps of transformation all the way through. We don't have those months of trying to agree on how we're going to interpret it. If that business unit wants to interpret it one way, fine, let them. If that business unit wants to interpret it another way, fine. We'll need to know when we look at the decisions the business makes, what they've done, but we let them go ahead, do some processing, do the analysis, and get the results. And in fact, this distributed platform around HDFS and the computation is being pushed into the next version of Hadoop. So Hadoop version 2, which went beta about 2 weeks ago, they're actually taking MapReduce out of Hadoop. Well, they're pulling it up. So what's left is a file system, job tracking system, configuration management system, all the kind of distributed processing and handling stuff that you need. But it can then be used by other distributed computation models. Now, this actually gets very, very exciting. Because, for example, there's a project called Storm. It used to be Twitter Storm, it's now Apache Storm, which is a real-time analytics, distributed real-time analytics platform. And that is being ported to run on Hadoop too. So you can imagine you've got your cluster sitting up in Azure, running your Hadoop baseline, and on top of that, you've got batch-based processing with MapReduce, and you've got real-time analytics. Someone starts hitting your website, you get a huge load on your systems. Okay, we'll just shut down our batches, pause them, and then we'll take that whole capacity and use that for our real-time analytics. And then when we want to, we can scale it back down again. Right? Over the same platform, the same storage system, same guarantees of reliability. Some very, very interesting stuff coming. Okay. Sorry. Let's have a look now at, I'm going to put my election spin doctor cap back on. Oops. And I'm going to use my tool of choice. I'm not going to show you the machine learning part or the categorization part of it. I assume that's already happened. I assume that the splitting up of the data into Hadoop via a MapReduce job has happened. I'm happy to show people that bit if they want to come after the talk. Now I'm going to use Excel. And I'm going to use Power Pivot. For those of you who haven't used Power Pivot, fantastic tool, especially because it runs in Excel 64-bit as well as the 32-bit version. So if you've got a 64 gig machine, you can put a lot of data in there because it's all compressed inside Power Pivot in memory. This isn't 64 gigs worth of data. So Power Pivot allows you to pull data in from various sources. In this particular case, I'm pulling 2 tables worth of data out of Hadoop. It's going to be the set of all the tweets with their times, IDs, user IDs. And I've got here 500,000 tweets. And then I'm also going to pull down all the unique users that are in those tweets. And these users I've then tagged as whether I think they're a Labour supporter or a Liberal supporter. I've also got their location, which city they're in. And then I've got my generated word frequency tables, which I've done in Hadoop. And there's about 1 million rows of that data. Okay, so the first question, there were 3 things I wanted to know as a spin doctor. One was, who are the people who are tweeting? Who do they support? And along with that, what are they saying? Then it was, when are they saying it? And then it was, where are they? Okay. Well, let's check, first of all, the distribution of the users on Twitter after we've categorized it, and we've done some normalization here as well. So we have a nice, strong peak in the middle. It looks like a nice distribution. We do a couple of cutoffs in our weighting so that we can say all the ones to your left are Liberals, all the ones to the right are Labour. You might notice there's a couple of peaks on the ends. Those are our seed data that we use to seed the machine. Oops. Oh, okay. Now, this is PowerView, and there's a bug in PowerView to do with colors, which they're working on. So let me fix this up. There we are. Okay. So my next question was, what are people saying? Now, you probably can't see that. Oh, does that help? So the question is, does our machine classification work? Do we think that it's picked the right terms or the right tweets for the right users, or the right following for the right users? Well, let's have a look. So we've got Labour supporters, they're talking about Abbott, I'm sure in a very complimentary manner. Hockey, talking about Liberals. They're also talking about internet, health, education, climate. Yeah, maybe. And then the Liberals, again, talking about Kevin and Gillard and real change. And yes, PM agenda. I think that's probably good classification. This is data captured, by the way, over the past 2 weeks, so up to Friday last week. So we now know what people are talking about in the different parties. Let's find out when they're talking about it. Okay. This is a distribution over the time we were capturing the tweets. It looks like something funny around the 7 o'clock mark during the day. So the top is the time of the day. I think there's a few people around the 3 a.m. that probably need to go to sleep rather than tweeting. And there's something funny around that 7 o'clock mark in the evening. Well, let's have a look what's going on. Okay, 7 o'clock. So August 21st and August 28th. Does anyone know what happened on those 2 days? Sorry? Yep, television debates, exactly. And just so happens to be about that time. So here we can see when people are talking, as well as what they're talking about, and also the distribution of who is talking when. It starts to become very powerful. Click on the 21st and see the full distribution for that day. Now, the last thing I wanted to know was, where are those people? Is there bias in the different areas in Australia? And you're probably sick and bored of maps by now. I think PowerView and PowerMap are the 2 new shiny toys that everyone's talking about. But I find this actually incredibly powerful. For example, we can see that up in Northern Territory, we've got quite a lot of Liberal supporters. Down in Tasmania, the Labour supporters. So the size of the circle here is the number of tweets, and the colouring is the loyalty, or who it's following. What's interesting about this is that the data ingress into Power Pivot is just straight through ODBC. So it's a direct query into Hive, which in turn does a MapReduce job over the raw data that's stored in the file system. So we're not having intermediate transformation steps, pulling it straight down into Excel. Okay. Yep. So we'll just finish off with a couple of points around data science. Okay. Just try and have a look at that slide and try and work out what it's telling us. Who here is still using Internet Explorer? Correlation does not imply causation. Well, most of the time. On a more serious note, in 1992, there was a research project in Sweden about health effects of living close to power lines. And they surveyed everyone who was living within 300 meters of power lines in Sweden, and going back 25 years. So they had quite a lot of data. And then they looked at 800 illnesses. And they said, are there any illnesses for which we find that living near power lines cause an increase in the illness? Now, as you think about this, it's a little bit subtle. And they found one. They found leukemia as an issue. And some people might remember there was leukemia scares around power lines. It was quite serious around that time. What people didn't know was they'd done 800 experiments over the same data looking for something that would work. Now, another way to explain this is called the Texas sharpshooter fallacy. A Texan takes his gun, has it at the side of a barn, and goes bang, 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 random shots all over the barn. He then walks up to the barn, he finds the best cluster of shots, and he paints a bullseye right around it. Then he invites his friends over and says, look what a good shot I am. Okay. So you be very careful. If you're doing huge numbers of experiments, you will find a result. It doesn't necessarily mean anything. You also need to test. So this is Google. So going back to the health theme, they do a very similar thing. They take their search results. Sorry, they look at what people are searching for and use that to predict flu outbreaks. And they started out in 2009. They worked okay for a few months, and then swine flu hit, and it just didn't work at all. So they recalibrated the engine. And it worked really well for another couple of years. And then in the last flu season in the US in end of 2012, it severely overestimated the flu impact. And that was actually the cause of a whole lot of media, which is sort of self-fulfilling because then the media causes people to search for it and the whole thing escalates. So you have to test any suppositions and any results you get. And be prepared to update your model as you're going along. Okay. Last bit, last slide. So in summary, collect everything, just don't store PII, personally identifiable information. Enhance your internal data systems with external data, but don't trust it. Do schema-free analysis over your information, but optimize that by pulling the data into your warehouses and effectively building indexes over it over time of stuff you do commonly. Continuously test Exactly the same way as you do unit testing in development, do data testing when you're doing data. You have to do testing. If you don't test, you've got no idea of the quality of the data, and you can put no weight in the results you get. And you've got to build not a software development lifecycle, but a data science lifecycle. Okay? And no presentation is complete without a Spidey quote. With great data, or great volumes of data, comes great responsibility. So use it wisely. Okay, thank you very much.